Hello, Gen Chem Oneers. Welcome back. We are going to cover Module 4 in this video. It looks like, based on my highly skilled organization skills, that I will be doing 3 lectures on this topic. So let's go and start with the first one. I am going to share my iPad. Okay, let me turn that off. All right, so in this section, we're going to be looking at molecules, ionic compounds, and nomenclature, which is basically how am I going to name these various types of compounds. So let's think about chemistry. How many different substances can possibly exist? I've got an entire periodic table filled with 118 or more elements that can potentially combine with each other to form compounds. Now we know not every element combines with every other element. There are rules to how bonds can form, but what we have is a great diversity of substances that we find in nature, which is a direct result of the ability of elements to combine with other elements to form compounds. Now let's look at hydrogen, which is an element, oxygen, which is another element, and water, which is H2O. There is a dramatic difference between the elements of hydrogen and oxygen and the compound water. That is pretty typical when we have various elements and then compare them with the compounds that they form. Water is composed of atoms of hydrogen and oxygen, but the substance H2O is much different physically than the individual elements of hydrogen and oxygen that compose it. For example, hydrogen is a gas at room temperature and ambient pressure. The boiling point is minus 253 degrees Celsius. It's explosive. Notice this is H2, so that's a diatomic molecular element. Oxygen is O2, that's also a diatomic molecular element. It has a boiling point of negative 183 degrees Celsius. It's also a gas at room temperature. And what we're going to compare that to is water, which is H2O. Water has a boiling point of 100 degrees. It's a liquid at room temperature. So when I think about the fact that when to use these temperatures to figure out what state it's in, anything above negative 253 degrees Celsius for hydrogen will be the gas form, right? Anything above negative 183 degrees Celsius for oxygen will be the gas form. Anything above 100 degrees Celsius for water will be the gas form. That's the boiling point, that transition between liquids to gases. So anything below 100 degrees and above 0 degrees, which is the melting point, means I'll be in the liquid phase. Now look at some properties. Hydrogen is explosive. If I put this in a balloon and I poke it with a burning poker, I'm going to get this big, huge pop and flame. Oxygen is actually necessary for combustion. I have to use oxygen in my gas tanks and in my heater at home in order to combust the various sources, gasoline or oil or natural gas or whatever you have. in order to burn that. And then water actually can be used to extinguish flames depending on the source of the fire. So again, here I have a mixture of hydrogen and oxygen molecules, elemental molecules. And in this balloon, they're gases because I'm at room temperature. And as this is a mixture, I can have any ratio of hydrogen to oxygen in this balloon. However, when I look at my water, which is going to be a compound, those water molecules have that fixed ratio. I have 2 hydrogen atoms to 1 oxygen atom. I always have H2O. I can't change that ratio. If I have more hydrogen atoms or more oxygen atoms, I don't actually have water. Remember, we talked, I think, about the difference between H2O and H2O2, which was hydrogen peroxide. This is a compound. It is a pure substance. That hydrogen and oxygen cannot be separated physically, like this hydrogen and oxygen elements, right? Molecules can be separated physically because it's a mixture. Here, that's a compound, that's a fixed ratio. The only way I can get my hydrogen and my oxygen out of water is to actually chemically react it in order to break it down to its constituent elements. Now, compounds are composed of atoms that are held together by chemical bonds. Chemical bonds are always electrostatic in nature. They're going to result from the attractions between charged particles. Remember, in my atom, I have the nucleus, which has protons, and around them, I have my negatively charged electrons. Well, these electrons will form bonds between 2 nuclei of 2 different elements. That bond, by nature, is going to be an electrostatic attraction that exists between the electrons, which are forming the bond, and those 2 nuclei of the atoms that actually form the bond. So chemical bonds can be classified very broadly into 2 types. I have ionic bond, and yes, you can think of ions here. Remember, I have positively charged cations, and I have negatively charged anions. And then covalent bond. This is a different type of bonding where electrons are shared, and we're going to talk about that in a second. So, when I have an ionic bond, I am having a bond that is forming between a metal and a nonmetal. I have full transfer of electrons from the metal to the nonmetal. So my metal goes to a positively charged ion, and my nonmetal goes to a negatively charged anion. This would be the positively charged ion is going to be a cation. So that metal becomes a cation because it lost negative charge, it lost electrons. So now I have more protons than electrons. The nonmetal becomes an anion because now it gained negative charge. It has more electrons than it has protons. Now I have these oppositely charged ions that are held together. Remember, opposite charges attract, and that's how I form my ionic bond. In the solid phase, what's really interesting about ionic compounds is that when they are in the solid phase, they form a lattice. This is a very highly ordered, regular 3-dimensional array, and I have alternating cations and anions. Now, when ionic compounds are dissolved, the ions will break up and become solvated. But in the solid phase, I have a very interesting very highly ordered lattice of alternating cations and anions. Here's an example. If I have sodium metal, which is sort of a soft, buttery-like metal, I can actually cut sodium with a butter knife. What I have is this array of sodium atoms. Remember, my electrons are loosely held. They kind of circulate around those positive ions, or those positive nuclei. So my neutral atom has 11 electrons because it's atomic number 11 on the periodic table. My sodium ion loses 1 electron, so I become sodium plus because I have 11 protons and I have 10 electrons. That gives me 1 more positive charge. This is chlorine gas. It's a nonmetal. My neutral chlorine has 17 electrons. It's going to gain that 1 electron. So this electron is being brought from sodium. It's being transferred from sodium to neutral chlorine. Now I have the Cl minus, which has 18 electrons. I had 17 electrons. I have 17 protons, right? But now I have 18 electrons, so I have a -1 charge. This is what sodium chloride looks like. I have sodium ions, which are these purple guys, surrounded by these larger chlorine ions. But what I have is this alternating, very highly ordered lattice of purple, green, and it sort of extends where my purple ions, which are the sodium pluses, are surrounded by multiple Cl minus ions. It's not just a 1-to-1 ratio. That's my lowest whole number ratio to give me net neutrality. But in the solid, every ion is surrounded by multiple ions of the opposite charge, and I form that lattice. This is what it looks like. You've probably all seen table salt. And those oppositely charged ions form these crystals, which is what you're seeing deep down on that molecular level. Those crystals are due to this lattice structure. Now, covalent bonds are a different type of bonding. These generally occur between 2 or more nonmetals. My 2 atoms are sharing electrons, which composes a molecule. So the single smallest unit of compounds that form molecular bonds is called a molecule. These compounds can also be called molecular compounds because their basis is the molecule. Again, this is electrostatic in nature because what I have is I have the 2 nuclei of the 2 nonmetals, and then I have the electrons that are being shared, and the lowest potential energy, the more stable positioning of these electrons occurs when they are sort of in between the 2 positively charged nuclei of those 2 elements. If they're not in between, right, that's more stable because those electrons are now balanced by those 2 protons, which happen to be positively charged. Now, covalent bonds can be considered sort of as a tug of war, right? If I have my neutrons, my protons, and neutrons, which form my positively charged nuclei, right? These nuclei are tugging on those electrons, those shared electrons, and it's kind of like a tug of rope. Do they want to go here? Do they want to go here? They kind of want to go everywhere, and that would be sort of the bond if this was considered one nuclei and that was considered the other. Compounds are represented by chemical formulas. This indicates which elements are present in the compound. And it indicates also the relative number of atoms or ions of each. This is my fixed ratio. So water always has 2 hydrogens to 1 oxygen. Sodium chloride always have 1 sodium plus to 1 Cl minus. Carbon dioxide always has 1 carbon atom to 2 oxygen atoms. Carbon tetrachloride always has 1 carbon atom to 4 chlorine atoms. So these subscripts tell us how many of those atoms of that particular element, or ion as the case may be, is present and in what ratio, right? That gives me the ratio of the relative number of atoms of ions of each of those elements. Now, chemical formulas can be categorized into 3 different types: empirical formulas, molecular formulas, and structural formulas. Each one of these types of formulas gives us different information. So I use the one that is necessary for whatever situation that I happen to be in. This is the lowest amount of information, and this is the highest amount of information. And then I sort of vary. So let me explain that. An empirical formula gives me the relative ratio of atoms of each element in a compound. This is my lowest whole number ratio. A molecular formula gives the actual number of atoms of each element found in that particular molecule. The empirical formula doesn't necessarily give me the formula of the actual molecule. Let's talk about this. I could have H2O2, which is hydrogen peroxide. This means in hydrogen peroxide, I have 2 hydrogen atoms for every 2 oxygen atoms. Here, my greatest common factor is 2. So the empirical formula is just 1H to 1O. That's the lowest whole number ratio in that particular common, or in that particular formula. So it's a 2 to 2 ratio that actually occurs. The actual molecular formula is H2O2. But because the greatest common factor in those subscripts is 2, the empirical formula is simply 1H to 1O, or HO. Let's look at another one. Here's this guy, B2H6. Again, I have a greatest common factor is 2. My molecular formula gives me 2 boron atoms to 6 hydrogen atoms. That's what's actually bonded. But my empirical, my lowest whole number ratio of those elements in the molecule is only 1 to 3. Now, if I have something like carbon tetrachloride, the only common factor is 1. Here, the empirical formula and the molecular formula are identical. Now, the structural formula is the best one. If you go on to take organic chemistry, the structural formula is really the only formula you're ever going to use. In this Gen Chem class, we actually can get a lot of information out of our regular molecular formula, so we use those a lot as well. But the structural formula is using lines to represent covalent bonds. And what's really important about this type of formula, it is showing atoms in a molecule and how they are connected or bonded to each other. Later on, we're going to learn that that bonded structural formula allows me to predict the molecule's geometry in 3-dimensional space. So if I looked at H2O2, what I know is the hydrogen is bonded to an oxygen. That oxygen is bonded to another oxygen, and that second hydrogen is bonded to another hydrogen. So I have H bonded to O, O bonded to O, O bonded to H. That is how the bonds form. I can't have O, O, H, H, or something else. I can't have O, H, H, O, right? This is how it's actually bonded, and there's reasons for that that we're going to discuss. This is another way I can actually write that. That's identical to this formula here. All I did was show my connections in a different way. Now, the type of formula we use depends on how much we know about the compound and how much we want to communicate. Structural formulas communicate the most information, and empirical formula communicates the least. Empirical formulas really don't give us much, but we're going to see I can use an empirical formula and other experimental data in order to figure out what my molecular formula is. As an organic chemist, I look at structural formulas and I use those almost exclusively when I'm in the field of organic, when I'm in that organic realm. In Gen Chem, we use molecular formulas a lot, and then later on in the class, we're going to look at how I can put those together in structures, looking at the bonding. Now, all of these molecules can be represented by molecular models. If you bought a modeling kit, or if you have one, it's really fun to play around with molecular models, and I can actually see what things look like in three-dimensional space. These are usually ball and stick molecular models, where in my kit I have these different colored balls, and then I have these sticks, which I can connect the balls to one another. And how these two connect reflects the molecule shape. So the molecular formula, or the molecular model, actually gives me an idea of how this thing looks in three-dimensional shape. The one thing is, in order to use a molecular model, you have to understand that those balls, which are representing elements, are going to be color-coded. And each color represents a specific element. So the white balls are always hydrogen. The black balls are carbon. This color blue is nitrogen, and then this red is oxygen. These guys are also specific, but again, in organic, most of the time we're looking at this piece. But since this is a Gen Chem class, if you do look at different models, you want to make sure that you understand that every different color and size of the balls that are in the molecular model actually corresponds to a different atom off the periodic table. There's also space-filling molecular models, which is designated here. That is actually going to more closely represent the best estimate for how a molecule might appear if it's scaled to size. So for example, carbon is a much larger element than hydrogen, and this is represented by the fact that that big black blob is a lot larger in its volume than those those 4 individual hydrogen atoms. So sometimes this is a useful information. Honestly, this and then the corresponding model, these are the most useful in terms of molecular models and bonding models. So here's a chart from our book that just gives you the various ways of representing compounds and then some examples. So for example, the molecule benzene This is the molecular formula, C6H6. I have 6 carbons bonded together in a ring. I have double and single bonds in that ring. And then I have another hydrogen connected to each one of those carbons. Now, I have a lowest common factor, or the greatest of 6. So my empirical formula just says in this molecule, I have 1 carbon to 1 hydrogen. That's my ratio. In actual, the molecule actually is these 6 carbons bonded to each other and to hydrogen. And it looks like this structurally. And then I have the molecular model and the space filling model. If you want to build a model of this, it's going to look like that. Acetylene, C2H2. Again, this is what it actually looks like. I have a triple bond between the 2 carbons, and then I have a single bond to each hydrogen. That gives me the most information. This would be what it looks like in a molecular model. Because it's C2H2, if I divide by 2, I get this CH as my lowest whole number ratio between the elements, and that's my empirical formula, and so on and so forth. So what you're going to be able to determine in this section is you need to look at, if you're given a molecular formula, you want to know if that molecular formula is the empirical formula or not. And then we're going to look at using these molecular formulas, these empirical formulas, to actually use experimental evidence and math to figure out what the corresponding molecular formula actually is. And that's going to be a topic that we get in the next module. But notice for sugar, which is glucose, or for the glucose molecule, I have C6H12O6. Right, divide by 6, I get CH2O as my empirical. Notice for ammonia, I don't have anything to divide by. So my ammonia empirical formula and the ammonia molecular formula is identical. And then these are what they look like structurally. We're not at that level yet. We're going to get there when we start looking at Lewis bonding theory and other theories later on in the textbook. Now, some elements are actually going to be molecules. Elements can either be atomic, where they consist of a single atom, or they can be molecular, where they consist of 2 or more atoms bonded together. Compounds can be molecular if they covalent bond, or ionic if they form ionic bonds, which is from a positively charged ion and a negatively charged ion. So my pure substances, remember, we talked about this later, can be broken down into elements and compounds. This, if they're covalent and it's non-metal to non-metal, I form molecular substances. This is ionic, and basically if it's a metal to non-metal, I can form ionic substances. This has molecules as its lowest sort of subunit. This has the lattice when it's a solid, so those are ratios. This formula unit, which is the formula, just gives me the ratio of positive and negative ions that give me a net zero charge on the entire compound. So for sodium chloride, it's a 1-to-1 ratio. I need 1 sodium atom for every 1 chloride, or I have 1 sodium plus atom for every chloride minus atom. And those two come together and they form that sodium chloride formula unit. So this is not a molecule, this is a formula unit. In the solid form, I form a lattice. This is not molecular, it's just a ratio. Whereas when I covalently bond, I actually form molecules as my lowest sort of unit that acts together. So I don't have an NaCl molecule that gives me a ratio of the charges of the ions in the crystal lattice. When I look at elements, these are what we're usually used to see. I could have a helium atom, I could have a carbon atom, I could have something like that. But there are molecular elements, and there are 7 of those. You want to know these. So it's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. 1, 2, 3, 4, 5, 6, 7. There's 7 diatomic. They have 2 elements or 2 atoms connected together. Because I have 2 atoms connected together, it's called molecular. So in nature, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are found as diatomic molecular elements. They're not found in nature as single atoms. They are found as diatomic molecules. So again, atomic elements, they exist in nature as single atoms as their basic unit. Most elements are going to fall into this category. There are these subset of molecular elements which you have to know. They do not have single atoms as their base unit. They exist as molecules where I have 2 or more atoms of the same element bonding together. That's why I can call them an element, because each atom in hydrogen is a hydrogen atom, right? So it's all hydrogen, but in nature, it doesn't just, it's not found as single atoms, it's found as atoms that are bonded together. So there are 7 diatomic elements, and you need to know these. When we start doing reactions, if something reacts with chlorine, it's reacting with Cl2 because that's how it's found in nature. It is not reacting with just Cl. So these are critical. If something is combusting in the presence of oxygen, the reactant in that reaction is O2, not O. You know anything about chemistry? When I have to use the law of conservation of mass in order to balance chemical equations and mass balance, in order to obey the law of conservation of mass, if I don't use how these elements are found in nature, I am not going to get the correct reactions written down on paper. Now, phosphorus and sulfur are called polyatomic ions. Phosphor in nature actually is found as P4. Sulfur is found as S8. Those are not as commonly used. These 7 diatomic elements are things that you definitely have to know and remember. And you can actually see that these 7 shown in yellow, most of them form this sort of upside down backwards L, and then there's hydrogen. But nitrogen, oxygen, fluorine, chlorine, bromine, iodine. This periodic table, notice the pattern. The pattern allows you to predict what's going to go on. And then again, I have this other L, which shows me other elements that exist as polyatomic molecules. These 7 are the ones you really have to know in yellow. So make sure that you understand those. And I think this is where we're going to break for the first lecture. And then I will be back shortly in order to continue on with Module 4. I will see you guys in a bit.